So let's create a camera. First, create input.rs file and put the model here at the top of the main function. I want the camera to move with W, A, S, D keys, and I want to zoom in and zoom out with Q and E. Let's first import the namespaces, and then we'll define the structs that we need and also the input plugin. So we need the prelude and fixed time step. Now let's define the speeds, the move speed and the zoom speed. This will be the maximum values that we will use for clamping our value. Now let us define two components. One will be main camera and the other will be the camera movement, which will hold the plane movement speed, so the 2D speed in X and Y direction, and the zoom speed. So the plane is vector 3, but we'll use just X and Y, and the zoom speed is a float because it only affects the scale, which is a float. Okay, let's go on with the struct of input plugin, and let's implement the trait plugin for input plugin, which forces us to define the build function. In the setup function, we use commands to insert different components, so basically to create entities. And we'll add the setup function as a startup system to our app. So let's go ahead and use commands to spawn a bundle. This is basically, it spawns an entity and also inserts many different components. So we're gonna spawn an orthographic camera bundle. And then we're gonna insert two components, main camera and our movement component, and also define the starting values. Now we will need two systems to handle the logic. One is camera movement and the other is camera zoom. In camera move function, we need to query for the transform and the movement component, but only those that have a main camera component. In our case, though, the query without the width would be enough because the main camera is the only camera that has the movement component. Also, we need to get the keyboard input resource so that we know which keys are pressed. Now let us define the direction vector, which we customize based on the user inputs. So we'll use the keyboard input resource to get the information about which key was pressed by the user. After we set the direction vector, we'll normalize it or 0, just in case if there is some division by 0 and we don't want to get the nans. So now that we normalize the vector, we want to iterate over all the components, so transform and movement. We could use dot single here because we know that there's only one main camera. And then we change the plane speed in the movement component and clamp it between the constant values that we defined earlier at the top of the file. After that, I want to, if the user presses space, I want to reset the speed to 0, and then we can change the transform translation with the speed. Okay, for the camera zoom system, we will need the following components: the camera movement component and the orthographic projection component. Only those components with main camera component. But again, as we said, the camera movement component is only on the main camera, so we could omit the width clause. And then we need again the keyboard input, which is a resource to get the keys when the user clicks the Q and E key. Okay, so now we'll use dot single mut instead of ether mute next, because we know there's only one instance of it. And then we'll unpack the movement and auto projection components. Then we adjust the zoom speed and clamp it. And after we adjust the zoom speed, we use the zoom speed to change the auto projection scale. And if the user pressed space, or when the user is at the limits of the zoom, we reset the speed to 0, so that if the user gets to the limit of the zoom, so he's zoomed out completely, we don't want the speed to be at the, I don't know which level, very high level, because the user would then need to hold the opposite key to zoom in for a long period of time to reduce that speed first to 0 and then into another direction. So to avoid that, we reset it when we get to the maximum zoom out or maximum zoom in. Now all we are left to do is to add these two systems to our app in the build function of the plugin. We'll add them with the system set function, thus we need to make a new system set. This lets us run camera movement and camera zoom systems at the desired time interval, since we can use the run criteria functionality. This is then all for the input plugin. Now we just need to add it to the main app in the main file. We can run it, but we won't be able to observe anything until we populate the cell with the cell entities. So let's go ahead and do that next. Alright, now we're diving into the good parts, the simulation. First, create simulation file and put the mode simulation below mode input. So Conway's Game of Life is a cell-based simulation that is governed by 3 simple rules. The cell dies if there are less than 2 or more than 3 neighbors. The cell lives if there are 2 or 3 neighbors. And the cell comes back to life if there are exactly 3 neighbors around it. And we are looking at the 8th neighborhood of the cell. We need the following resources and components to make our simulation work. Cell component with a state field, which is an enum with the following possible values: alive, empty, or dead. Resource for holding the word coordinates of a mouse click for setting the cell on or alive. Resource for holding the word coordinates of a mouse click for setting the cell off or empty. Resource for sprites to show off different cell states. Resource to hold a boolean to know if simulation is currently running or not. And at the end, we'll also add Bevy labels so that we can run systems in sequence, one before the other, if we wish to, and we do wish to run the storing of mouse coordinates before we actually use them in our cell interaction systems. While I was explaining which components and resources we will be needing, I was also importing the namespaces, so most of them are for the events and main camera for screen to word coordinates transformation, and the obvious prelude and fixed time step. I'm also setting the constant sprite size to 32 pixels. Before we actually start, let's go define the simulation plugin, implement the plugin trait, and define the setup function where we'll use commands to spawn entities and insert components. Let's go over the resources and components that we talked about before. And after we go over the implementation of resources and components, let's add them to the app with their initial starting values as well. Here we will also insert the clear color resource, which basically provides the default color, the default background color. we will now go over the grid size, so the 2D grid size, and spawn the sprite bundle, set the transform based on the X and Y values, and insert our cell component. After we are done with this, we'll also use the asset server to load the 3 different sprites and store the handles in our sprite images resource. Let's go to the main file and add the simulation plugin namespace and add the plugin to the app. Now let's run the app. And as you can see, now we can finally test the camera, zoom, and movement systems as well. Now let's talk about cell interaction. We want to be able to click on an individual cell and either set it on or set it off. This means we'll need two Bevy resources, which we defined earlier, to store the mouse click world coordinates. Since the mouse click is in pixel coordinates, which start in the bottom left corner of the screen, we need to translate these to the world coordinates where 0, 0 position is in the middle of the screen. And we also need to account for the orthographics camera projection while doing this transformation. So we'll need two systems and a helper function to be able to interact with the cells. One system will be responsible for transforming mouse screen coordinates to world coordinates and storing them into the resource we mentioned earlier. And we only do this if the simulation is not running or active. We do this storing of the coordinates for both erase and draw, and this depends on which mouse button the user clicked. The other system is taking the option and consuming it. It then goes over all the cells and checks if the mouse click is contained in any of the cells. So basically we check if particular cell was clicked. If it is, we change the state to appropriate state. So if the left mouse button was clicked, we change it to the alive state. If right mouse button was clicked, we change it to the empty state. Let's start with the helper function for transforming mouse from pixels to world coordinates. So first we need the position, right? The camera transform, the window, and projection. We'll calculate, we'll transform the center to the bottom left, and we have to account for projection scale in each of these steps. Okay, so let's write the function for setting the cursor world position in our resources. We'll need to query entities for transform and orthographic projections with the main camera. We'll need the resource for input and our resources behind mutable references and the is running resource to check if the simulation is running. We'll get the window with Windows get primary, and we'll try to get the cursor position from it. Then we'll use the main camera.single, which you already know. So with the window cursor position, we got the position of our cursor in the pixel coordinates, and we'll transform it to world coordinates and store it if the mouse button was pressed. So either left or right mouse button. Alright, let's get to cell interaction. We'll need to query for the following components: cell, handle image, and transform. And we'll need the resources such as our mouse world coordinates positions, draw and erase, and sprite images. Also, we'll need to know if the simulation is actually running. Then we'll consume these coordinates, so the mouse draw and mouse erase, and check if the simulation is running or if either of these resources is some, so basically different than none. And if that's the case, we go over all the cells, check if one of the cell contains the click, and if it does, we change the state. And this depends on the actual click. So if we are consuming the draw or erase. Cell bounds basically checks if the click is in the cell bounds. So we have XY, which is our click position, center of the cell, and the dimensions of the cells, which is basically 32 divided by 2, so 16 pixels. And if the condition is true, we change the sprite and change the state of the cell. Now let's first implement, before we do the simulation, the event reader systems, which are basically really straightforward. So let's do the exit the game, set simulation, and the unset simulation. We use the event reader, and we use the events that we defined in our user interface file. And then we just use iter next and check if the event reader is some, and if it is, we change the state of our resource. Okay, simulation. So if the simulation is running, we go over all the cells and copy the information into the vector, so their state information. Then we read from this vector and change the cell states accordingly, based on the rules mentioned at the beginning of the video. And that's it. So as you can see, we are going over all the cells, all the cell components, and pushing to live grid true or false based on the state of the cell. When we go over the cells again and we compute the x and y and use this x and y to iterate or to go over the neighborhood of the cell and count the number of neighbors who are alive. And then based on this information, we change the state of the cell accordingly. Now let's add all these systems to the app. First, let's go with the event reader systems, and then let's add two system sets. One system set will be the cell interaction stuff, so the mouse clicks and setting and unsetting cells. We'll use the run criteria to run them at a certain time interval, and then we need to add the system labels, and these labels will be used to run certain system before another system. So we can use .after, .before for the systems. So let's check that out. And after we are done with this, we'll add another system set, which will be just the system simulation. And that will run at another run criteria / fixed time step and run after the cell interaction setting label. So that's it. As you can see, you can click and draw whatever you like. You can also remove with the right button and play the simulation. and as you can see, the dead cells are colored pinkish, and the empty are of a darker theme. So yeah, hopefully you liked the tutorial. It was kind of straightforward. I know Game of Life isn't particularly hard, but if you found it useful, please drop a like, or any constructive criticism is always helpful. So yeah, other than that, see you around and have fun.